Welcome friends, in the last video we had talked about the MOSFET, how it is being used as a switch. In this video we'll be elaborating more on this topic, how the MOSFET is being used as a switch. Suppose this is the source, this is the drain terminal, or suppose we draw it in the reverse way, the gate terminal, the drain terminal and the source terminal, right? NMOS, let's just suppose. So the signal moves, the electrons move from the source to the drain, so we can say the current moves from the drain to the source, right? So the gate terminal will control whether it will move or not. So basically we will say that this is the drain terminal, this is the source terminal, and the gate will control whether the switch will be on or whether it will be off. Now we will consider one more thing, that I suppose all of you know that for the MOSFET to be acting as a switch, it should not be in the saturation region. The condition for saturation region is that VDS should be greater than or equal to VGS minus VTH. So for this purpose this should not be the case. So for this purpose VDS should definitely be less than or equal to VGS minus VTH. So suppose taking this source as a common part, we can say that VD should be less than or equal to VG minus VTH. That is, VD should be less than or equal to VG minus VTH. So this is the equation that we come across. So let us say that we are taking an NMOS. Okay, we are taking an NMOS. This is the MOS structure. Right. So what is the maximum value that we can give to this drain? If this is at a voltage VDD, the voltage VDD, so this potential, this voltage should at max come to a potential of VDD minus of VTH, because if this potential, that is the drain potential, gets above VDD minus VTH, then the MOSFET would reach the saturation region, and if it reaches the saturation region then it would not work as a switch. So we need the drain terminal to be less than VDD minus VTH. So if you use an NMOS, we can say that if this is the VDD mark, the input voltage can be always less than VDD by VTH level. Any input less than VDD minus VTH is definitely appreciated by the switch, but any input more than VDD minus VTH shall be rejected and shall not be considered as an input to the switch. So an NMOS can work only for input voltages on the drain which is less than VDD minus VTH. Now suppose we talk about PMOS. It's a bit different out there. That is, VSD should be greater than or equal to VSG minus VTH, right? So here VD minus VD should be greater than or equal to minus VG minus VTH, or reversing it, VD should be less than or equal to VG plus VTH. That is for saturation condition. But here we do not want it, so it should be VD should be greater than or equal to VG minus plus VTH, or we consider here as VTP for the PMOS. Okay, so for a PMOS, if we draw the region of operation, if this is the 0, okay, this is 0, because for PMOS we say that the VD should be at the 0 level. Okay, and so if this is the VTP level, any signal greater than VTP is appreciated by the switch, but any signal less than that is not considered as a new input to the switch. So we can see that a NMOS works when the input is less than VDD minus VTH, whereas a PMOS works at an input greater than VTP. So if these two work separately, these are not being able to serve the entire region. Sorry. So what we do is we use a thing called a Cmos, okay, which is complementary MOS, which is an NMOS and a PMOS. The configuration becomes something like NMOS, PMOS. Here we give the V in, and here we take the V out. Okay, so here we give the clock to the NMOS, and to the PMOS we give the clock bar. This is the circuit. So what happens is, if this is the 0 mark, this is the VDD mark, the NMOS works for VDD minus VTH marks, and the PMOS works for VTP higher than VTP marks. So both working together, less than VTP mark, the NMOS works. Within VTP and VDD minus VTH, both the MOS work, and greater than VTH, the PMOS works. So there is no such region where a MOS is off. So both the MOSes together help in getting the work done. That is, in this region the NMOS work, in this region N plus P work, and this region the PMOS work. Okay, the resistance curve becomes like this and like this. Why does the resistance curve become like this? The reason is that in this region the PMOS is not working, so we do not consider PMOS. As we are moving to the right side towards the VDD minus VTH side, the switch is slowly switching off. Sorry, and thus the resistance is increasing. In the middle portion it is not a straight line because the difference of the mobilities between the holes and the electrons, and in the right portion the resistance decreases because of the inverse region of the region 1. So this is all about MOS complementary switch or the Cmos switch. Thank you for watching. In the next video we'll talk about some different types of switches and the clock feed through effect. Please like and subscribe my channel.